let us solve a problem as an example. As I said before, polonium is the only element that uses a simple cube structure, and the polonium has an atomic weight of 208.982 grams per mole. And also, we know that the radius of the polonium, of the atom of polonium, is equal to 190 picometers. So now let us find the density. So if the radius is 190 picometers, it means that this is 190 times 10 to the minus 12 meters. Here, the mass, I can say that the mass will be equal to the number of atoms times the atomic weight divided by the Avogadro's number. So this will be 1 atom times the atomic weight, which is 208 times 982 grams per mole, divided by the Avogadro's number, which is 6.022 times 10 to the 23 atoms per mole. And atoms cancel, moles and moles. And my final answer is 3.4703 times 10 to the minus 22 grams. And the density then will be equal to the mass divided by the volume, which we said that can also be defined as NA over NA divided by the volume of the cell. Although the radius is in meters, I want to convert this into centimeters to have the density in units of grams per centimeter. So this is also equal to 190 times 10 to the minus 10 centimeters. So here, if I replace the whole mass by 3.4703 times 10 to the minus 22 grams divided by 8 times the radius, and the radius is 190 times 10 to the minus 10 centimeters to the power 3. So my final answer is 6.32 grams per cubic centimeter. And that would be the density of polonium. Now let us talk about the body center cubic, or BCC. In a body center cubic, we have the open structure that will look like this, very similar to the simple cubic, plus the fact that we have an additional atom. So here we have this atom that is in the center is an additional atom. So representing this as the actual portion of atoms that belong to one unit cell, so we'll have a total of A. Again, we will have 1, 2, 3, 4, 5, 6, 7, which is hidden, and 8. So 8 times 1/8 of an atom, that is equal to 1 atom, plus the fact that we have one additional atom in the center. So we have 1 atom here, which means that we have a number of atoms that is full atoms equal to 2. So now we have 2. So that changes. What else changes with respect to the SC? Also, let me change the color. If I use red, now here I have my radius of the atom. However, they don't touch. So I can't simply say, because there is an empty portion here, I can't say that A, which is this distance, will be equal to 2R anymore. But something I can notice here is that if I draw a diagonal that crosses one point, that would be 0.1 with 0.8 of the unit cell, this is equal to 1R plus 2 radius, that is the diameter of the center atom, plus the radius of this atom. So I have a total of 4R. And then I can demonstrate later, let me change this, that by using the fact that this diagonal is equal to 4 times R, A can then be found to be equal to 4 times the radius of the atom divided by square root of 3. So this will be different from the SC. Now, the volume of the cell then that is VC, will still be equal to a to the power 3, but this time a is equal to 4 times r divided by square root of 3 to the power 3. Well, the occupied volume, Vs, is equal to 2 atoms times the volume of one sphere. So that would be 4 times 4 over 3 pi r to the power 3, which means that Vs is equal to 8 over 3 pi r to the power 3. And also here, the atomic packing factor, APF, which is Vs over Vc, this time will be equal to 0.68. So which means that 68% of the cell is occupied. And the only thing that we need to define now is the number of neighbors. So the number of neighbors are going to be equal to 8 this time. And the elements with this kind of structure, that is BCC, we have among them, we have iron, we also have manganese, chromium, vanadium, niobium, molybdenum, tantalum, tungsten, lithium, sodium, potassium, rubidium, cesium, barium, radium, and europium. Now we have more elements. And let us solve an example. So if we have an example where we want to calculate the theoretical density of iron, so that would be density of iron, we can use the same equation. So we know that the density of iron will be equal to the mass divided by the volume of the cell unit. And as before, we can write this as N, the number of atoms, times the atomic weight divided by the volume of the cell over the number of Avogadro. And here the volume of the cell is equal to a to the power 3, which is equal to, if I go back, that is 4r over square root of 3, 4r over square root of 3 to the power 3. Now for item, we do need some piece of information. So first of all, the radius of the atom is equal to 0.124 nanometers, while the atomic weight for iron is 55.845 grams per mole. So replacing R, then the volume of the cell can be calculated as 4 times the radius, that is 1.24 times 10 to the minus 8 centimeters, since we want to get cubic centimeters, over square root of 3. And this is equal to 23.54 times 10 to the minus 24 cubic centimeters. And therefore, the density of item can be then found as the number of atoms that we have in a BCC structure is equal to 2. So I write 2. So we have 2 atoms times the atomic weight, which is 55.845 grams per mole, over the volume of the cell, which is 23.54 times 10 to the minus 24 cubic centimeter times the Avogadro's number, that is 6.022 times 10 to the 23 atoms per mole, to finally have density of iron equal to 7.882 grams per cubic centimeter.